All right, so the last section we're going to look at is what's called angular velocity, and it's 2.1 part 3. So what we're going to look at is basically how we can describe the speed of something that's spinning. Okay? And the unit that we generally use is radians. Okay? There are other units. You can use degrees. You can also use revolutions. But in our book, when they don't tell us what unit to use to describe the speed of something moving in a circular path, the default unit we'll go to is radians. So when would you measure the speed of something spinning? Well, if you had maybe certain tools. I don't know if you're familiar with like a Dremel. It's like a drill, but it's not. It just spins at higher speed. You can measure the amount of RPMs it spins at. Some of them are variable, so you can go from maybe as low as 5,000 RPMs, maybe up 10 or 15,000 RPMs. That's how fast the tool spins. If you have a tire and it's on a machine, like to balance it, the machine may have to get it up to a certain number of RPMs to simulate it being on a car. All right, so it might spin at 100 RPM, well, that'd be kind of slow, maybe like 500 RPMs or something. So there's two kinds of ways you can measure speed. Okay, the speed of something spinning is different than the speed of moving in a straight line. Okay? And I'll talk about why you need to measure the speed of something spinning a little bit different than a straight line. And you can call that angular speed or angular velocity. Either term for us is the same thing. Okay, so let's look at this disk. Okay, and the disk has 3 dots on it. Does anybody remember there is a formula you can use to find distance? It has a D, an R, and a T in it. Does anybody remember the formula that I'm thinking of? Yeah, Eliana? No? Yeah? Right, distance equals rate times time. That means to find out how far you've traveled, you take the speed you're traveling at, and you multiply how long you've been driving at that speed. And that tells you how far you've gone. All right, so distance equals rate times time. So then, if I rearrange it for R, and get R by itself, what would R equal? Yep.
Distance divided by time.
Right. If you know how far you've traveled, and you know how long it took you to travel that, you can figure out your average speed. Okay. All right, so now, let's look at that circle with the 3 dots on it. Okay, I'm going to rotate that circle one time, and I just want you to kind of watch what happens to the 3 dots. They're all revolving. And that was 1 revolution. So out of the 3 dots, this column 1, 2, and 3, which dot traveled the farthest? Yeah? Yeah, the 3rd dot traveled the farthest because it was the one that was away from the center the most. Right? So dot 3 traveled the farthest, dot 2 the 2nd farthest, and then dot 1, if it was perfectly in the center, it almost looks like it didn't move at all. Right? But that's the problem. Dot 1 was still moving. It was just spinning in place. So you can't say that the speed of dot 1 is 0, because if you want to measure it, it is actually spinning. So we need a way to describe how it's moving in place. Okay? And that's what this is going to do. All right, so we all agree dot 3 traveled the farthest. Now, how much time did it take for dot 1, dot 2, and dot 3 to travel the path they traveled? Like if you compare the time it took dot 1 to do its thing, dot 2 to do its thing, and dot 3 to do its thing. How do all those times compare? Yeah?
No.
They're all the same. Okay? They all traveled 1 full revolution in the same amount of time. Is the size of the revolution different? Yes. And that's the problem. If dot 3 traveled farther than dot 2 in the same amount of time. What does that mean about dot 3? Dot 3 traveled farther, but it did it in the same amount of time as dot 2.
It's moving faster.
It must be moving faster than dot 2. So thinking of describing speed this way gets complicated when it's something spinning, because every point from the center of the disk to the edge would be traveling at a different speed. It would have to be. There's no way dot 3 can cover more distance in the same amount of time unless it's going faster. So then how would you describe the speed of that? Would you describe the speed from dot 3? Would you describe it from dot 2, dot 1? Like where would you describe the speed from? Right. It gets confusing. But one thing that is consistent is we can say all of those dots made one revolution. Let's say it took me like 3 seconds to do that. They made one revolution in 3 seconds. The size of the revolution is different, but they still all made one revolution in 3 seconds. Okay? So that's why when we describe the speed of something spinning, you use either revolutions, radians, or degrees. Okay? Any question on that? All right, so what we're going to look at is basically how do we convert between, let's say, something traveling maybe feet per second to miles per hour. Okay, so we'll start with something like that. And then eventually we want to get into how can we convert angular speed, which is something spinning, into linear speed, which is something moving in a straight line. Okay, so how could you imagine that? Well, imagine you had a tire spinning on a machine, right, at 1,000 RPMs. It's not actually going anywhere. It's just spinning in place. But let's say all of a sudden the tire falls off the machine and it hits the ground. Right? What's going to happen? Well, there's nothing in the way. The tire's going to hit the ground, and all of a sudden it's going to take off. I basically want to know what would happen if a tire spinning at 1,000 RPMs fell off the machine, hit the ground. How fast is it going to be rolling on the ground? That's an example of converting angular to linear. Another example would be if you had like a rope, right? And you were swinging it in a circle. Maybe there's a rock, or some kind of weight on the end of the rope. You're swinging it. All of a sudden, as you're swinging the rope breaks. Okay, what's going to happen? Well, you were spinning it in a circle, so it wasn't traveling anywhere. It was just spinning around you. When that rope breaks, all of a sudden that object that was tied to the end of the rope, it's going to take off and go in a straight line. What's happening is the angular speed of its spinning is instantly being converted into a linear speed because the rope broke and it's going to take off straight. So we're going to look at a couple examples of that towards the end. Okay, so linear speed, there's lots of different units we use for that. You can take anything you use to measure a straight line distance. Feet, inches, centimeters, kilometers, millimeters, miles, divided by, and then any unit you use to measure time. Hours and seconds are probably the most common. All right, so there's lots of different ways we measure linear speed. But angular speed, there's really only 3. Degrees, radians, revolutions. The time unit for angular speed, that could be anything you want. Seconds, minutes, hours, days. Hours and seconds are probably the most common there as well. And the way that we're going to convert between different units is the same way that I taught you how to convert between radians and degrees. If you have degrees and you want to get rid of it, you have to think of where that unit would go in the other fraction. If it's in the top on this one, where would degrees go on that one to cancel it out? Yep, it would go on the bottom. And then, we'd multiply and start doing out whatever we have to do. The important thing to understand is if you put the same unit in the top and in the bottom, it will cancel that unit out. And you'll end up with a new unit. Okay, that's called dimensional analysis. So we're going to start just by, we're going to practice converting like days to seconds or seconds to days. We'll try something like that. So we'll start just by looking at a time and see if we can change that from one unit to another unit. Okay, so we're going to try to change days to minutes. Now, 3 days, okay, is that a speed? No, that's not even a speed yet. Okay. Next, we're gonna look at a speed. That's a speed. A speed has a distance and a time with it. This just has distance. Okay, so it's a little bit easier. So first thing we're going to do is write down 3 days. I usually make it a fraction. All right, so now we want to convert days to minutes, but we want to go 1 unit at a time. Okay, I don't know how many minutes in a day off the top of my head, but I do know how many minutes in something else, and that's the next unit down from days. Okay, so what's the next unit coming down from days, getting closer to minutes? Yep. Hours. So the first thing we're going to do is we're going to change to hours. So we're going to make days disappear. We're going to turn it into hours. Where would we want days to go in the second fraction so it cancels out days in the first fraction? We want days in the bottom. And we want hours in the top. Now we have to fill in a fact here that is true. It can be any fact that you know about hours and days. It just has to be something that is true. Okay. Can someone give me a fact, a true fact, that relates hours and days?
24 hours.
Yeah, 24 hours in 1 day. That's, if you put 48 hours in 2 days, that would also be correct. But I would put the simplest one you can think of. Okay. So now, if you multiplied straight across, you would have a unit of hours. Okay. But we want minutes. So now we want to get hours to cancel. Where would hours go in the third fraction to cancel out? Yep. Go in the bottom. We're going to put minutes in the top. And now we need to fill in a true fact about hours and minutes. Anything that's true. Yep.
60 minutes in an hour.
There are 60 minutes in 1 hour. Okay. Now we have hours in the top, hours in the bottom. Look at the unit we're left with, minutes. That's what they want. So now the last step is to just multiply all of that together. So 3 times 24 times 60. So it's 4,320 minutes. In 3 days. Okay, and that's, again, from a different lesson, so it's actually example 1. It's our first. I think that was our first one. Any questions on that? All right, so there are certain conversions that you would need to know, all right? The ones that I would not give you on a test. So conversions that you need to know are like how many seconds in a minute, how many minutes in an hour, how many hours in a day, days in a year. You would need to know how many feet in a yard, which is how many? 3? Yep. How many feet in a mile? Uh, 5,280. Yep. So there's 5,280 feet in a mile. I would say those are the conversions you'd need to know. How many inches in a foot? I think I said that. Yeah. I wouldn't expect you to know like how many grams in a pound. Right? That's now you're converting from metric to standard, so that's a strange conversion. Okay, it's not a nice number. How many centimeters in an inch? Same thing. That's metric to standard. Those aren't ones you'd have to know. But The basic one's about time, I just said, and length. All right, so now let's try another one. Okay, this one, a little bit different. We're converting 50 feet per second into miles per hour. This is a speed. It's a speed because it has a distance component and a time component. What does that mean? 50 feet slash second. What is that like if you're trying to actually describe to somebody how fast that object is moving? What does it mean?
Every second, whatever's moving 50 feet.
Right. Every second, the object moves 50 feet. So we're going to write that as 50 feet in 1 second. Okay. And now it's like we're really doing two problems. First, we have to get feet into miles. Then we have to get seconds to hours. So we have to fix both parts of that. It doesn't matter which one we do first. So let's deal with the time unit first. Okay, let's change seconds into hours. But what unit are we going to go through in the middle as we change seconds to hours? Yep, minutes. Okay, so first let's change seconds to minutes. So I want seconds to disappear. Where would seconds go in that fraction? Go in the top. And what would go in the bottom? Minutes. So now seconds is gone. And what could I fill in for a fact here? Yep.
60 seconds.
60 seconds in 1 minute. Okay, if we stop there, we now have a speed in feet per minute. We want hours. So now let's get rid of minutes. Okay, where's minutes going to go this time? It's going to go in the top. What's going to go in the bottom?
Hours.
Yep, hours goes in the bottom. And what's a fact that connects minutes and hours?
60 minutes in an hour.
60 minutes in an hour. Okay, minutes in the bottom, minutes in the top. Okay, if we stop there, what would be my unit now on my final answer? I would have feet per hour. So I'm close. I have feet per hour. I want miles per hour. So the last thing I need to get rid of is feet. Okay. Even if we don't know how many feet in a mile, we should, because we just said it, we should know where feet is going to go. Where is the label feet going to go? It has to go in the bottom because we're canceling it out. And the unit we're going to put in the top? Miles. Okay. So now, what is the fact that we can fill in there? So yeah, 1 mile is how much? 5,280. Okay, so 1 mile is 5,280 feet. Feet in the top, feet in the bottom. All right. So now we're left with miles in the top, we're left with hours in the bottom. That's exactly the unit that they want, miles per hour. Okay, we got to multiply that out now. Okay, so the way I would multiply it is I would do everything in the top first. 50, 60, 60. So that's everything in the top. And then divided by, I'll type it in the way I would do it if these weren't all ones. I really only need to divide by 5,280. But if there were other numbers here that weren't ones, I would do it like this. 1 times 1 times 1 times 5,280. That's how I would type in all the numbers in the bottom. I don't need to type in the ones. I'm just showing you how to do it. Okay. The parentheses there would be important. So it ends up as 34.09. Okay, and what's my unit on that?
Miles an hour.
Miles per hour. Yep. There are 2 units that you might see abbreviated with 3 letters. Okay, you might see MPH for miles per hour. You might also see RPMs. That stands for revolutions per minute. Okay, those are probably the most common ones you'd see abbreviated with 3 letters. But I'm going to try to stick to writing it like this, because I don't want you to get a question wrong because you're confused on what an abbreviation means. Okay? Like, this isn't like meters per hour, it is miles per hour, at least in the US. Okay? But I'll write it like that. All right, any question on that one? All right, so now, so far we've worked with units that you should be pretty familiar with. Okay. So now let's try working with an angular speed. Okay. And this is going to use a new unit, well, at least new to us this week. Okay. We have an object that is spinning at 200 radians per second, and they want us to change it to revolutions per minute. Okay. The steps to do this, it's no different than the steps we just did up above. All you have to do is set up your fractions, so your units cancel, but you have to know the conversions. Okay? So like how many radians in a revolution, that is something you need to know from Monday, or maybe Tuesday, whenever we talked about converting degrees to radians. All right, so let's start with what we've got. We have an object that is spinning at 200 radians every second. Okay. For a lot of people, that might be kind of hard to visualize because we're not that used to radians, but hopefully if we change it to revolutions, that'll put it in terms that are more familiar. All right. Is either one of my units here the unit they want in the final answer? No, they don't want radians and they don't want seconds. So let's fix seconds first. Okay. We want to get rid of seconds and we want to get minutes. So can somebody give me the whole conversion I would have to put next to it? Yep.
60 seconds on the 1 minute.
Yep, 60 seconds in a minute. And now we've got a speed of radians per minute. The next step, we want to convert radians to revolutions. Even if you don't know the numbers, you should be able to tell me where radians is going to go. Okay. Is radians going to go in the top or the bottom? Yes, it has to go in the bottom because we want it to cancel. And what's the unit we're trying to convert to? Revolutions. Okay, now we need to fill in the fact there. How many radians in 1 revolution? If you get stuck, think of how many degrees in a revolution, and then convert degrees to radians. Yep.
Was it 2 pi?
2 pi. Yep. It's 360 degrees. Or 2 pi. We need 2 pi because we're trying to convert from radians. We're not trying to convert from degrees. So there's 2 pi radians in 1 revolution. Okay. What unit is going to cancel out now? Yep, radians is gone. What unit am I left with in the top? Revolutions. And the bottom? That's exactly what they want. Yep. Okay, so let's type that in. So I'm going to do 200.
Wait, so where did you get 2 pi radians?
So where did we get 2 pi radians from? Yep. Yeah, if you convert 360 degrees to radians, that's what you would get. Yep. It's kind of like saying, well, where did you get 12 inches from when you say 12 inches is a foot? Just a fact. You just have to memorize 12 inches in a foot. You just have to memorize there's 2 pi radians in 1 revolution. Okay, so now we're going to type all that in. We've got 200 times 60 divided by, I'll show you what happens if you don't put parentheses around that 2 pi in a second. 1,909.86. So that's, I mean, I don't know, depending on what you're talking about, I mean, that's pretty fast. I mean, if you were spinning in a circle almost 2,000 times in a minute, you'd probably be a little dizzy. So it's reasonably fast. If you divide that by 60, you could figure out how many times per second that is. So that object is spinning 31 times a second. It's pretty fast. So what would happen if you didn't put the 2 pi in parentheses? Okay, if you did the top, 200 times 60, and then you did divided by 2 pi. I thought I had it. Divided by 2 pi. You did not get 1,909.86. When you do it, let me show you what happens. When you do it the second way, which is wrong, it took 12,000. It divided that answer by 2, and then it multiplied that answer by pi. That is not what you wanted. Okay? You wanted 12,000 divided by 2 pi. Okay? But if you don't put it in parentheses, the calculator will literally think you want that. Take your answer, divide by 2, and then multiply that by pi after. So that is not what you want. That's why I always, well, it's further up on the screen, but that's why I put parentheses around the 2 pi. Okay. Any questions on that? Because that stinks. To get this far, you've done the whole problem, and you just typed it in the wrong way. Yep.
I got, even like after I did that, I got 6.2, but the answer that you had was different.
So you did the top first, right?
Yep.
And then you hit enter.
Yep.
So you got 12,000. And then if you do divided by, and you put parentheses just like that, well, and you actually put a pi symbol. Let me get rid of that. So just like that.
Yep. Oh, I multiplied. I just realized I got it.
Yeah. Okay. So yeah, any other questions on that? All right. So that was converting an angular speed, something spinning, to a different angular speed, something still spinning. Okay. The one we did before that was a linear speed to a linear speed. What we want to look at now is making the jump between the two. What if something's spinning, like a rope, like maybe on a machine, that rope breaks, whatever it was spinning is now going to shoot off in a straight line. Okay. That's what we want to start to look at. All right, so now let's say that we had a wheel that has a radius of 18 inches. And this wheel is spinning at 1,850 RPMs. That's revolutions per minute. If you didn't know what RPM stood for, I would tell you that, because I don't want you to mess that up. Okay, so it's 1850 revolutions per minute. Part A is doing what we just did in the last problem in reverse. It's taking a speed in RPMs and changing it back to radians per second. It's the same thing we just did, but in reverse. Okay, I want to try part B, which is different. Find the linear speed of the wheel by measuring a point that's right on the circumference. So I'm talking about if this is spinning, I want to know the speed of that point right there. Another way to think of it, this tire is on a machine, it falls off the machine, it hits the ground, doesn't lose any traction, and all of a sudden it was spinning. How fast is it going to be rolling on the ground? That's what we're figuring out. All right. So what what did they give us for a speed that we can use as our starting point? Yep.
1,850 RPM.
Right. So we know that this is spinning at 1,850. And we want to break that unit out into revolutions in the top, minutes in the bottom. All right. Well, one easy thing we can do is they want seconds. They don't want minutes. So we can deal with that right away. What's the fraction that's going to get rid of minutes?
1 minute is over 60 seconds.
So 1 minute over 60 seconds. Okay, so that's the easy part. Now we've got revolutions per second instead of per minute. Now we want to get rid of revolutions. We don't even know numbers yet, but we should know where. Where would revolutions go if we want it to disappear? We want it to go in the bottom. In place of revolutions, what unit do we want? Feet. We want feet. That's what we have to figure out. How many revolutions, or how many feet in a revolution? Okay. So how many feet are there in a revolution? What do you think? How many feet in a revolution? Yeah?
I was going to say whatever the circumference is, circle.
Yeah, it's not an answer that's the same all the time. It's like asking you, how many feet to the doorway? Which doorway? What are we talking about? So it depends on the situation. So how many feet in one revolution? Are you talking about a revolution like that? Are you talking about a revolution like that? Like what kind of revolution are we talking about? They gave us some information that told us how big of a revolution we're going to be making. What did they give us that's going to tell us the size of the revolution in this problem? Yeah, they gave us the radius of the tire. So we can figure out how big one revolution is. Okay, that's what we need to measure, that part in blue. Pretend like that's a piece of string in blue, and then I cut it and I straighten it out. I want to know how long it would be. We already said it, but this is a revolution, but in terms of the circle, it's the what? It's the circumference. So all we have to do is figure out the circumference of that circle, and that will tell us how many feet in a revolution. All right? So the first thing we should look at is they want feet. They gave me the circumference in inches. So off to the side, let's just fix that. 18 inches is how many feet?
1.5.
It's 1.5 feet. If you're not sure, you just take the number of inches and you divide by 12, and that tells you how many feet you have. Okay. So now we know the radius is 1.5 feet. What's the formula for the circumference of a circle? Yep.
Pi r squared.
Pi r squared, that's the area. So that is a formula we used yesterday.
Was it 2 pi r?
2 pi r. Okay. And what is the radius that they give me for my wheel? 18 inches or 1.5 feet. I'm going to go with 1.5 feet because they want feet in the final answer. Okay. If we multiply that together and leave it exact, what's 2 pi times 1.5? Yep. 3 pi. Yeah, that's 3 pi. 2 pi times 1.5, it's 2 times 1.5. That gives you 3, and then pi. So how many feet are there in one revolution of this tire? 3 pi. Right? So basically, if this tire was on the ground, and you put a mark on like the sidewall, and you rolled the tire one time until that mark ended up back on the ground again, and you measured the distance between where you started and where you stopped, the tire would roll that many feet. That's how many feet in one revolution of the tire. 3 pi feet. So that is a conversion you need to figure out every time. It's not like asking you how many minutes in an hour, how many hours in a day. Those are the same. Those never change. But how many feet in a revolution depends on the size of the tire. Okay. So now revolutions and revolutions cancel. And let's multiply it out and see what we get. All right, so we've got 1850 times 3 pi. So that's my numerator. And now I need to divide that by 1 times 60 times 1. So it's just dividing by 60. So that's 290.6 if we round up. 290.6. And what's my label on that?
Feet per second?
Feet per second. Okay, so how fast is that? Let's see. Are you getting out of the way? If it falls off the machine and it's out in the hallway and it starts coming towards me, do I get enough time to move? Well, we did another problem that had feet per second. Where was that one? Right here. We did 50 feet per second. Okay. 50 feet per second is 34 miles an hour. This is 290 feet per second. So it's almost 6 times as fast. 6 times as fast would be 300 feet per second. We have 290, so we're pretty close. If you are going 6 times as fast as 34 miles an hour, then the object's probably coming at you at about 200 miles an hour. So,
Jeez.
you think you can get out of the way?
Oh yeah, oh yeah.
200 miles an hour? Maybe if it was like 15 football fields away, you'd have enough time. Maybe. But if it's across the shop and it's coming at you at 200 miles an hour, I don't think you're getting out of the way. It's pretty fast. All right. Any question on that one? All right, so that's converting angular to linear. Okay. All right. Any questions on any of the examples we did? This was actually example 2, and that was really example 3. 1, 2, 3. All right. So I'm going to pause it here. I'm going to put up the homework and then also put up a list of topics that are going to be on the test.